Okay, so this is a video on recreating the paper published in AID 2020, entitled Reinforcement Learning with Quantum Variational Circuits. And so I am, in fact, first author on that paper. And although I didn't make the code public, I've gotten a lot of inquiries about the paper, about working with it, recreating it with it, and so I'm you know I rewrote the code to be a little more friendly, and so now I'm making that publicly available, and I'm going over it now. So just to explain it, go through it. It's not exactly identical to what was in the paper. I made actually some improvements, but um, the gist is all there, and it's basically the same. I just changed, some hyperparameters and stuff. So, oh, I just realized that that screen wasn't even sharing, but I can do this. There we go. And we can see this is the paper that we will be recreating. And so specifically, we're not doing all of this. We are just going to look at recreating this one line, or replicating one line, which is this green line here for DQN and cartpole. That's basically, yeah, that's all we're doing is just that line. And so basically we're just going to be doing the non-double version of this algorithm. So first off, I'm assuming that everyone has some sort of level of quantum understanding. So I'm not going to do any background on the quantum side, really. We all know superposition, entanglement. We know how to work with TensorFlow-Quantum. I talked about that before, and there's basic videos on quantum computing, which I'll probably do more on. But reinforcement learning, not everyone is familiar with, at least coming from the quantum side of things. So I'll go over that just briefly here. And so reinforcement learning is a pretty big field now. It's growing a lot. There's a lot more people getting involved with it. And basically it's distinct from supervised learning and unsupervised learning in that it's basically an agent interacting with an environment trying to maximize some reward. So, numerically, we can say that the RL problem is a maximization policy. So we want to pick the policy that maximizes the expected, that's not a very good E, the expected value of the sum over the length of the environment. So that's basically what it is. Basically, we're just trying to maximize reward. What does that look like? There's a lot of different techniques to do this. We use the Q learning function. So the Q value of a state action is basically the expected reward given some sort of initial conditions. And so I talk about this a little bit in my AI and society talk. So if you want more RL, I recommend you check that out. But basically, we can just recursively update the Q value via Q of S comma A equals RT plus the max of Q of S prime A prime. Oh, this is a gamma right here. And so basically we take the reward after a given state, and then we approximate future reward, and we can update. So you can think about the loss function from here is just subtract this side, and it's the difference of these terms. And so there's a lot of problems with Q learning. It's a moving target that you're constantly trying to approximate, because this is like the goal. If you're thinking of supervised learning, this right here is the goal, and this is your approximation. So this is sort of, if you have like labeled training data X, Y, this is the Y. That's probably a bad example actually, but all we have to think about is this is our target. This is what we want to learn, but it's being updated by itself within the target value is this, parametrized sort of function, which, is a problem, and it makes, there's certain instabilities in this algorithm. So how exactly do we do DQN? Just as a quick little, how do I make a new page? I seem to have forgotten up there. So we just have a neural network or quantum variational circuit that takes as input some states. In this case, I'm doing cartpole, so it will be 4 numbers. 1, 2, 3, 4. So some sort of array goes into function approximator. And then this function approximator outputs, in this case, 2 values for the approximate Q values. So this is going to be some number. This is basically Q of state A1, and this is Q of state comma A2. So and then we just simply pick the higher one of these, and we can interact with the environment and calculate the loss. So this really isn't meant to be a big overview of Q learning. This probably is hard for you if you don't have a lot of background or any sort of understanding, but that's just sort of the quick overview. And so in terms of the mechanics of the quantum problem, all this amounts to is we have to first encode this classical information into the QVC, which we do in a linear manner, scaling O of n, which means that we have 4 qubits, which means how do we get the numbers after operating on these 4 qubits down to 2 values? We use 2 different approaches. You can feed these values into a dense layer at the end, or you can use a quantum pooling operation, which we've seen before in the XOR problem. And in this case, we use quantum pooling to take 4, and we pool down to 2. And then we have this is basically the same thing. And so that's sort of the overview. I will now skip on over to the code. Do that. Here we go. So here's the code already written. You can see a whole thing, less than 200 lines. Pretty easy, and it's not even optimal. I just wrote this up real quick. You're welcome to play around with different things in it. I'll link it in the description. So we have GEM, OpenAI GEM is a common set of environments, standard imports. So now let's actually get into the code. This is just the agent class we're defining. So we make the qubits here. I'll get to the function approximator in a second. This is a really high learning rate just because I wanted fast convergence, because it isn't the fastest code to run. I can convert this into if we could serialize this sort of graph functionality, then it might be faster, but it does take, I don't know, maybe 20 minutes to fully run. And so we use the Atom optimizer with this pretty high learning rate, buffer size of 10,000, batch size of 32. And then this is the replay buffer, sort of a separated form of it. So actions, rewards, done, next state. Then these are the Q-learning hyperparameters. We have the gamma, which is, these are values may be different from the paper 2 of 9.9. We have initial epsilon of 1.0, epsilon decay of 0.9, and a min of 0.01. So that's pretty standard stuff in RL, nothing too exciting there. Now we get into the make function approximator. So our readout operators are just going to be, this is a fancy way of just making 2 readout operators. It reads out on qubits 2 and 3. And so that's because we pool all the qubits 1 and 2 and 2 and 3 down into 2 and 3. And so, or I should say 0, 1, 1 and 2, 2 and 3, down into 2 and 3. And so we just read out these 2 values for the action space. The inputs, the standard string, differentiator, typical parameter shift. We initialize it with zeros. That's pretty common. And then we just make the model. And that's all we have to do. Now, let's look at this. Before we get to convert data, let's look at how we make the circuit. So we have 48 parameters that we're updating. You can see the math here. There's 4 qubits. There's 3 weights or numerical values per qubit. And there's 3 layers. So that's 36 values. And then we have 2 pooling operations, each of which has 6 values. So that's a total of 48. So we make the 3 layers, then we do 2 pooling operations, pooling these into 2 and 3. We can see here, and we'll show the circuits. And so to look at each layer, we can see it's pretty simple. All we do is apply C0 gates to every single pair of qubits. And so we can see that this results in, for 4 qubits, this results in 3 qubits. Okay, you probably noticed a sudden change. Yeah, I just had to fix a bug that I realized was in there. Everything else is the same. I just changed the line that we were currently on. So as I was saying, you apply the C0 gates, and then you simply, for each layer, it's just Rx, Ry, Rz on each qubit. And so this just creates that, because there's 4 qubits, you're iterating by 4. And so if we want to see what this circuit looks like before we continue on, I print it before the pooling operations, because the pooling operations are so horizontally long, it kind of messes up the whole thing. We can add, let me add a window capture and cmd.ext. We can see that when I run it, the circuit will print right here, and we'll see 3 layers of, well, hopefully it will print right here. I guess I don't know what's happening right now, but normally we would see 3 layers of the circuit. Maybe if I just, okay, I don't know what just happened there, but we are good. We see the circuit slightly different from the paper, but we have the C0 gates here, the Rx's, Ry's, Rc's, and 3 layers of this sort of unit. And we can see it's training right now. We can see average reward, iteration reward, etc. That's the epsilon for epsilon greedy exploration. So now we can cancel that program so it doesn't slow everything down, and go back to this. So now that we have this circuit together, we can go back and we can look at how we convert the data. So this is a really simple technique we use. It's similar to computational basis encoding, except it just relies on the, it doesn't convert the numbers numerically into binary. It's sort of like converts the sign into binary, so the sign of each of the input values. So we say, if it's negative, we don't rotate. If it's positive, we do rotate. And so then for each qubit, we just rotate for these 4 values. This is just a flag that's useful for training. So we have that convert data, the details of which you can see in the original paper. And then we have the typical, adding stuff to the replay buffer. Then the actions is defined via epsilon greedy. So we pick a random number, and if it's less than our defined value, then we just take a random action. Otherwise, we greedily choose the predicted max action. And then we have the training setup. And so this looks big, but it's a lot of just, management. So we have the indices. We basically randomly select from the whole replay buffer, and we just convert them into their associated data types, converting to tensors, changing to floats and ints. This is just to make sure it's easy to work with. Sometimes it'll throw errors, and so this is all just sort of to make sure there's no errors being thrown. And so then we just so we're keeping track of the gradient here. We make predictions. Then we have this. If we look back at the, let's see, if we look back at this, we see that this right here is y. And so we can see that this right here, the reward, is the same as y. And then we make our prediction. Then we just care about the specific actions that we take. So we just gather the actions that we want, and then we subtract them. We square. This is basically just mean squared error right here. So we subtract them, we square them, and then we take the average. And this is the mean squared Bellman error. We calculate the gradient, we apply the gradient, and we do epsilon decay. So this is pretty standard stuff for reinforcement learning. The quantum stuff is all up here. And then this setup is, I just for this quick setup, did 200 iterations, a rolling average size of 50, a learn delay of 1,000. So we create the environment for cart pull. This is just, keeping track of things. We get the action, we step, we remember to reward, we go through this whole process. We print out at each time the what episode we're on, the average reward, and then we plot the final result. And so this part is pretty standard. If you've ever worked with OpenAI Gym, this code is probably, you have your own version of, bookkeeping, all of this stuff. And so in the end, if I can bring up the, nope. That's the one. This is what the result looks like here. And this isn't exactly the same as the paper. We can see it does reach about 100 in a similar time frame, but it decreases. This isn't always happening. You can increase or decrease the replay buffer to mess with this. But it is worth noting that catastrophic forgetting is a common problem in deep Q networks, or at least very simple ones. And so you can see it starting to increase again, and that's why it's always important to take an average of runs. And that's why in the paper you'll see there's an average, and on average it does okay. It's just in this particular instance doesn't do great. I could rerun it and get a better sort of average. I just didn't feel like doing that, and so that's pretty much all there is to it. The code's pretty simple. This is mainly a review for people who know both about quantum machine learning and about reinforcement learning. It's not meant to be like a general introduction to both. And so hopefully this code can help people implement it, recreate it, play around with it. You can read the paper for the exact hyperparameters and differences between this implementation and that. But overall, it's very similar. And just as a last note, I recently made a Discord server actually for quantum machine learning. I'm a member of one for reinforcement learning, and I found it a great way to communicate with other people who know different things. You can learn a lot. You can teach a lot. It's just a great resource. So I'll also link that in the comments. You can join or not. I think it's just very useful to have a more relaxed or more communicating forum for discussion of quantum machine learning, because there's not a lot of great, you can go to Stack Overflow, but that's not great. And if you don't have some sort of professor you can just ask, it can be hard to get information on such a niche field. And so, yeah, I made a Discord for that. Feel free to check it out.